if you've got a magnet, you might want to measure magnetization, right? And it always surprises me, well, it occasionally surprises me that some other laboratories, high magnetic field laboratories, don't seem to measure magnetization at all. So I will give a big shout out to Eun-Sang Choi, who leads our magnetization program here at the MagLab. Most of the slides that you see contain material from him. So two things I want you to keep in mind as we go through the talk today. Every measurement perturbs the system. The question is how much, okay? And the second point, every measurement measures something. The question is, what are you measuring, right? So as you go through, I want you to sort of think about those things in the back of your head, and if we have time, we'll talk about that at the end. And sort of each of these things, you know, each of the measurements, there's many different ways to measure magnetization, and each of them has positives and each of them has negatives, and some of those things depend upon what you're perturbing and what you're actually measuring. So, all right, some basics just to start off with. You guys know that we use B, H, and M in your textbooks. So in SI units, B is equal to mu times H, or mu naught H plus M, where M is the volume magnetization. Or mu naught 1 plus chi, where chi is the susceptibility times H. In CGS units, it's B H plus 4 pi M, where we basically set mu to 0. Sorry, mu to 1. So B is the magnetic flux density. Essentially, it's the magnetic field through a certain area. Magnetic induction. When we're measuring magnetic induction, we're typically talking about a susceptometer. Okay, H is the magnetic field strength from an external source. All right, and then the M is the magnetization from a sample. So that tends to, when you're measuring M, you're using a magnetometer. You're measuring the magnetic moment. So the units B in CGS units are Gauss. In SI units, they're Tesla, or Webers per meter squared, and the conversion is 1 Gauss equals 10 to the minus 4 Tesla. A Gauss, the Earth's magnetic field typically is around, anybody know? Half a Gauss, that's right, that's right. So we live in about a half a Gauss magnetic field. So when people talk about the effects of 60 hertz magnetic fields on your body, when you do a somersault in the Earth's magnetic field, you just had more magnetic induction on your body than the 60 hertz typically that you're around. So H is measured in Oersteds, or amps per meter, and there's a conversion factor that's kind of ugly. And M is measured in EMU per centimeter cubed, or amps per meter. M, small m, the magnetic moment, where you divided out the volume, is EMU per centimeter, or amps per meters cubed. And the conversion factor is over here. So for H, much, much greater than M, B is equal to mu naught H times T, with a conversion factor of 10 to the 4th Oersteds per Tesla. The other thing that we need to remember is that all of these quantities are vector quantities. In particular, M is a vector, okay? So if you're measuring a sample, it has a vector, and it could be pointing in some direction. And you need to think about, how does this affect your measurement? A lot of times people don't think about that, okay? So that's something that's glossed over in a lot of measurements, and in some cases it doesn't matter. But in some cases, it really does. All right, so the first set of methods are induction or flux techniques. These all use Gauss's law, where you have the flux is equal to the magnetic field integrated over a certain area. And you have Faraday's law, where you have the voltage is equal to the change in flux over a unit of time. Okay, so if you have a sample with some magnetic moment and you move it up and down through a ring, you're going to induce current, or you're going to induce EMF, voltage, around that ring, and you can use that to measure the magnetization. Okay, so all of these techniques are, dadgummit, technology. All of these techniques involve some variant on that. So the first one we'll talk about is a SQUID. This is a Josephson effect device, a superconducting weak link. I'm not going to talk about the physics of Josephson junctions, but basically if we take two weak links, so if you have a superconducting material and you have a weak link here where you have a tunneling current that goes across the device, and you have some flux in the center, you bias it with a current, you get an IV curve that looks like this. So it's small currents, it's flat, it's superconducting, there's no voltage across it, but at some current, it turns on, the voltage jumps up suddenly, and you get this big change for a very small increase in current, okay, across that device. So if you bias that device at this little point down here, and now all of a sudden you put a flux, a little piece of flux, a flux quantum, through that device. If you start at zero at the bias point, and you start putting that flux quantum through there, you get a very large increase in voltage across your device. Okay, but it's cyclic. As you put the rest of the flux quantum through there, you get a decrease in the voltage across the device. And then you put another flux quantum in there, it increases and it oscillates, okay? So this is a wonderfully sensitive way to measure microscopic amounts of flux, okay? And if all you were going to do is use a SQUID in this configuration, it would be not very useful at all. But really smart people figured out that you can take that SQUID loop with the bias circuit sort of taken out of it, and you can have an input coil around that SQUID loop with connected to a big coil where your sample goes through. And then you have a feedback loop over on this side. So the idea is that you bias this device at some point here, and then as you put a flux through from your sample over here, as you're moving the sample through this, you're inducing current and therefore inducing current through here and making a magnetic field. And then as that magnetic field penetrates the SQUID loop, you get a big change in the signal. But now I use that change in signal to provide a feedback, and I null out. I put current through this loop, so I null out the flux inside the SQUID. Okay, so now I have an extremely sensitive device that has a very wide range of operation, a wide dynamic range. Okay, so this is a flux transformer. Typically, you're going to, people who make real SQUIDs use flux transformers that are second order gradiometers. There are all kinds of different designs out there for third order gradiometers and fifth order and I don't know what. But basically you're going to have a loop where you have a plus, a loop in one direction separated by another loop in another direction, and then further down you have loops in the opposite direction. So as I move a sample through this, I get a negative voltage, a positive voltage, a negative voltage. Okay, so this subtracts out the effects of gradients and provides a little more accurate measurement of the magnetization of your sample. So typically you're going to run a known sample through there, then you can calibrate this device. If you have a commercial SQUID, it will have already been done. But then you put any other sample through here and you measure the magnetization. Okay? Some effects that you have to worry about is the size of your sample. Okay? There are shape effects for your sample. There's some other little things. So if you're worried about the absolute magnetization, then those are effects that you need to kind of think about. Most people don't care about absolute magnetization to that precision. And so most people ignore things like size effects or shape effects. So this is a quantum design SQUID magnetometer. This is a schematic of one. So typically there is a magnet up to about 7 Tesla. I think that's the biggest magnet that's quantum design still sells for an MPMS. There's a second order gradiometer in there. You put your sample on the end of a rod. Typically you're putting it inside of a straw, a non-magnetic straw. Some people have found that some straws are actually magnetic, so make sure that you use a non-magnetic straw. If you don't want to use one from quantum design because they're expensive, you can get a straw, but then make sure that it's actually non-magnetic. Measure it. So that rod is connected to a linear motor that drives the sample up and down through those coils. There are heaters and thermometers that allow you to adjust the temperature of your sample inside of this SQUID setup. And the actual SQUID is down here in a niobium shield. Obviously, if the magnetic field from your big magnet up here couples into your SQUID, you're screwed, okay? So you can't have that. So these things are in niobium shields so that no magnetic field from the measurement up here couples into the SQUID down at the bottom. And that's why typically these things are limited to 7 Tesla. Okay? If you go to higher magnetic fields, you start to put flux through the niobium shield and you ruin your measurement. Okay? So we have talked about trying to make a SQUID for high field measurements, and it's possible, but it's difficult. So the next type of measurement that lives in this category is a vibrating sample magnetometer, or a VSM. The simple version of it is an extraction magnetometer, and this is where you put a sample. You have 2 pickup coils that are oppositely wound. You put a sample on the end, you put it in a magnetic field, and you just jerk this thing out. As you jerk it out, you get a signal that depends upon how fast you jerk it out and the magnetization of your sample. Okay, so there are some labs in the world that use extraction magnetometers. It turns out that instead of just using an extraction magnetometer, instead of just jerking it out once and then putting it back in and jerking it out and then putting it back in, you can vibrate the sample up and down through those pickup coils, okay, which is what a vibrating sample magnetometer does. So this is the first generation, the very first VSM, and they actually used a loudspeaker to drive the sample up and down through the pickup coils at the bottom. So the voltage is equal to the magnetization times the amplitude times the frequency that you're driving this thing at, okay? So the nice thing is you can measure the absolute magnetic moment can be measured. The driving mechanism can be a motor, it can be pneumatic, it can be piezo actuator. Lots of different ways to do this. You can have feedback and phase-sensitive detection, so you can use a lock-in, which is very nice. You can have capacitive detection, eddy current sensor, servo motors. So you can make these things extremely complicated and extremely sensitive. At the MagLab, we have a VSM that works in fields up to 35 Tesla and temperatures down to at the high end of helium-3 temperatures. Okay? So the frequency it vibrates at is 82 hertz. Its amplitude is about 0.1 millimeters, and its sensitivity is around 10 to the minus 3 to 10 to the minus 5 EMUs. Okay? So compared to a SQUID, that really sucks. But for most magnetic materials, it's just fine. It works very well. So typically, in our setup, you have a sample tube. There's heaters on that sample tube. There's pickup coils that are 46 gauge wire wound in 3,000 turns on the outside of the sample tube. So the sample tube is filled with exchange gas at the temperature that you want your sample to be. You put this thing on a table above the magnet, and you isolate it from vibration, because obviously you don't want the vibration from the system coupling in. It has to be aligned very closely. If your sample rod rubs on the sample tube, the outside, it screws it up. Okay? It looks like a response from your sample instead of a response, instead of just rubbing on the outside of the tube. So it's extremely sensitive, so you have to align this thing very well so that the tube is straight up and down. But if you're very careful, and we can be, you get great measurements with this. So there's a sample rod, there's a G adjustment, XY adjustment, driving head up above it. Okay? So this was originally a Lakeshore system. I'm not sure Lakeshore makes VSMs anymore. Right? Do they? Yeah. So questions about that? Okay. We have another VSM setup that's up to 9 Tesla, 1.4 K, and this uses a high-pressure self-locking pressure clamp. So one of the nice things about a VSM is you can actually measure things in a pressure cell. So this is a high-purity, cobalt-free beryllium copper. So if you're going to measure the magnetization of something very tiny inside of this thing, you want something that's as low in magnetization as possible. And this material is very low in magnetization because it was specifically made to be cobalt-free. The sample size can be up to about 1 millimeter. The sample mass is quite small. Clamp mass is 13 grams. But you can, at relatively modest pressures, can get quite nice data as a function of temperature and pressure. So the next technique that's in this category is AC susceptibility. So now instead of you moving the sample up and down and the motion driving, yes? Yeah, sure. I'm not really sure. I think it's where the seals blow out. And so it depends on how good you are at making those seals. I suspect that it's not much above 6 kilobar. Do you know, Tim? I don't. Yeah, yeah. So this is probably pretty close to the maximum there. So it is a variation of a piston cylinder clamp. So AC susceptibility, instead of driving the sample up and down through the coils and that being what induces current in those coils, now you leave your sample in one place and you have an outside coil that drives an AC field, and now I have 2 other coils that are co-wound, one plus and one minus, okay? And that outside, you have a mutual inductance between the inner coil and the outer coil. And so the AC field that you put on here induces a current on the inner coils, okay? In an ideal situation, if you have no sample in here and these are perfectly wound, then when you turn on this AC field on the outside, you get absolutely no signal on the inside, because those 2 coils are oppositely wound, they're perfectly balanced, and so you don't see anything. So now when I put a sample on the inside of one of those fields, I know that whatever signal I get is due to the sample and not the coils, okay? And so this is an induction method. It's a change of flux given by oscillating the magnetic field. We're oscillating the field by an AC current in a solenoid. The current can be written as H0 cosine omega t. And then the signal is proportional to the change in flux. It's proportional to the change in magnetization, okay? Which is, lets us measure the complex susceptibility. So one of the nice things about this measurement is that we can measure time-dependent magnetization, okay? So if you have something that is dissipative, okay, or is sensitive to relaxation time, for example, a spin glass below the ferromagnetic transition, or a superparamagnetism below its critical temperature, or domain wall movement in a ferromagnet, Any of those things are time dependent. And so by varying the frequency of your AC field here, you can explore the time dependence of the phenomena that you're looking at. Okay? Yes?
So SQUID glass has some very slow long time scale.
It can, right, at very, very low temperatures, it can be days or weeks, right? At higher temperatures, it can be much faster. So, yes, but you can, obviously, you're probably not going to run an AC susceptometer with a time constant of days or weeks, but you can measure spin glasses at much higher temperatures and shorter time constants. So an AC susceptibility, the details, so the current is I times cosine omega t. You're going to get a background voltage because these samples are not perfect. So without a sample, I'm going to get something that depends upon the mutual inductances of these two different coils. When the sample is put in one coil, I get a certain voltage. When the sample is put in the other coil, I get another voltage. And then I can combine all of this and get a signal that's proportional to the number of turns, the cross-sectional area that I'm measuring, okay, the filling factor, how much my sample fills that cross-section area, the oscillating external field, and the complex susceptibility of the sample, which obviously is what I'm interested in. Okay, so a couple of things to think about here. If you want to do AC susceptibility, a couple of things that are important is you have a filling factor, okay? If you're trying to put a tiny, tiny sample inside of a big coil, you're going to have a sucky filling factor, okay? And you're not going to get a very good measurement. So having coils that are sized to your sample can be very important. Or having a set of coils, okay, that I can use for various different size samples can be very important. And here we have a set of coils, various different coils that we can use for various different samples to try to maximize the filling factor. If you're doing this yourself and you have your own sample, okay, wind the coil to fit as close as possible onto your sample. Okay, so in the end you get a setup like this, so you can get the a calibration factor on the bottom, and you have your susceptibility, and you have your driving field. Okay, so a couple of things to look at here. The final signal depends upon the driving field. It's inversely it also depends linearly upon the frequency. I'm sorry, that's the filling factor and the frequency that I'm driving this thing at. So the higher in frequency I drive it, the better my signal is going to be. Okay? What happens when I drive something in a magnetic field at higher frequencies? Any ideas? I mean, at low temperatures, any temperature really, but what's that? It heats, that's right. We get eddy current heating. In fact, we were making a measurement once in the helium-3 system, and we didn't want to wait for all the helium-3 to boil away, and so we turned up the frequency and we turned up the amplitude, and the helium-3 boiled out of the system really quickly. Afterwards, we took the dewar out of the magnet, and we had scorched the tails on the dewar. So not even at low temperatures, even at room temperature, driving an AC magnetic field will cause heating. Okay, and we have a setup in one of our. Do we still have that? Yeah, Cell 7 has a separate bore tube that goes in, so that this driving coil is in the cooling water of the magnet. So we can really turn up the amplitude and really do some serious oscillation. And then all you have to do is put your pickup coils down around your sample. So at low temperatures, though, if you go to lower frequencies and higher amplitudes, you can win. At least that's the theory. In practice, your susceptibilities depend upon the frequencies that you're measuring at. And so you kind of have to play around and find the sweet spot where you get the best signal into these coils and out of your sample. So there's balancing techniques, countermatched, counterwind coils minimize the out of the non-magnetization signal from these coils. You can sample translate, so if you put your sample on a rod and put it in between the two different coils, you can translate between the different pickup coils and automatically take out any effect of mismatched coils. You can then do a subtraction of an AC waveform similar to that of an empty pickup coil. Okay, so then you can use this to balance the external compensator without a sample, use a differential amplifier for sample and balance signal. So you can calibrate these things with a paramagnetic standard, aluminum, platinum, Tungsten salt, ferromagnets, superconducting materials. If you care about calibrating things, you can also buy calibration standards from NIST that are absurdly expensive but are calibration standards. Some other issues to worry about: skin depth for metallic samples. Okay, you can drive this thing at high enough frequencies that the magnetization does not fully penetrate your sample. Okay, so the skin depth goes like the resistivity over the frequency, and so at very high frequencies, the AC signal is not actually getting all the way inside the sample. So you want to go to lower frequencies with very good metals. You can get eddy current effects, heating, phase shift. So we talked about that. All right, so some applications for this, looking at phase transitions. We talked about spin glass, superparamagnetism, domains in ferromagnetism. So this is looking at the frequency dependence of your signal. So here is something where you're measuring the susceptibility, and you're driving this at different fields or different field strengths. Here is a spin glass. You see a very sharp transition, and you can see as a function of temperature the different peaks for that spin glass depending upon the frequency that was used. So you can use this. It works quite well for superconductors, for de Haas van Alphen oscillations. Can be used in extreme conditions, low temperatures, high pressures, and high or low fields. Okay, so this is an example of a diamond anvil cell where the pickup coils are wound external to the diamond, but very close to the inside of the diamond anvil cell. So here's the primary coil. So here's the secondary coils, and see, instead of having a secondary coil and then the counterwound secondary above it, they put them inside and outside. Okay, so obviously the areas are different, so you have to have a different number of turns, but you can then balance those by having different turns, and then so there's an AC susceptibility. So this, you can see this anti-ferromagnetic transition under pressure and a superconducting transition with the diamond anvil cell. All right, any questions about the AC susceptibility? So this is the MagLab high field susceptometer. The sample position is controlled by a stepper motor at the top, so we can put the sample in different positions inside of the either coil. We use a current calibrator, Valhalla current source is used to drive the AC current. Lockhead technique is used for the detection. We have a ratio transformer for balancing the different coils, so if something's off, we can balance it at room temperature with the ratio transformer, and then use the field modulation technique with a modulation coil for de Haas van Alphen measurements. Okay? So any questions about that setup? All right. So all of the measurements we just talked about you're able to, I won't say easily, but in a straightforward way to calibrate the signal that you're getting from your sample, okay? So if you care about measuring absolute magnetization, it's straightforward to calibrate what you're measuring and get the absolute magnetization of your sample. Some of the techniques we're going to be talking about now are much more difficult to get the absolute magnetization of your sample, but they can be extremely sensitive, approaching the sensitivity or exceeding the sensitivity of a SQUID. So these are methods where we're using the torque or force to measure. So when you put a magnetic particle in a magnetic field, you have some potential energy. It wants to move. There can be a torque associated with a magnetic moment that's in a magnetic field. It wants to align itself with the magnetic field. There can be a force associated with a gradient. So if I put a magnetic moment above a magnet or in a magnet's gradient, there will be a force associated with the dot product of that magnetic moment and the field. So the first of these techniques we'll talk about is a torque magnetometer. It's a very simple technique, very easy to use, and sometimes hard to get it right. So basically, if you have a sample and you put it on a diving board that's some distance above another plane, and you put it in a magnetic field, there's going to be a torque that's associated with the cross product of the magnetization and the magnetic field. If you're in a field gradient, if you're not in field center, there will be a force on the diving board as well. Okay, so if you're at field center or if you're off center but in an extremely homogeneous field, that force will be zero, and you'll have a torque which is proportional to the deflection of the beam up here. So you can cut a diving board out of a thin metal film, and you can measure the capacitance between this upper plate and the bottom plate, and you can get sensitivities better than 10 to the minus 8 EMU. We can take a piezo cantilever, we'll talk about this more later, and get sensitivities better than 10 to the minus 11 EMU. Okay? And because these things get more sensitive in high magnetic fields, they have sensitivities that can exceed the sensitivity of a SQUID. SQUID people will not believe me, but it's true. Okay, so if I have a single crystal represented by this, and I have its magnetization is pointed at some arbitrary angle, and I put it in a magnetic field, okay, there is a torque then that is associated with all of this crap out here. So I get a torque then that's associated with the angles between the magnetic field and the moment in the sample. Okay, so you have a shape effect for this. You can have a torque for a non-isotropic or non-spherical sample, and so all of these things make it difficult to measure the absolute magnetization of a sample. But you have exquisite sensitivity. So here we have a metal film cantilever. It deflects because of the sample that's placed on it. You can increase the dynamic range or increase the sensitivity depending upon how thick you make your cantilever, depending upon how long you make your cantilever, depending upon where you place your sample on the cantilever. Okay? So if I have a really massive sample, I can make a cantilever out of really thick beryllium copper, really stiff material, and then I'm going to not be as sensitive, but I'm going to have more dynamic range. Okay, I'm not going to worry about that cantilever completely flopping over. Okay, we have had some researchers that made cantilevers out of gold leaf. Okay, so very sensitive. I think they were pretty crappy cantilevers. You know, they don't have very good restoring force. So you want to have something that's springy and not something that's shear-y like gold is, okay? But they did use gold, and they were extremely sensitive, and they had excellent measurements. But the next time they came, they didn't use gold. So, yes?
What are the sizes, like a case of this?
Typical thicknesses, I mean, they're foil thicknesses, you know. Yeah, so you can, and the one you can cut these things out with scissors, you know. Yeah. Yeah, yeah, yeah. So they're so simple, I can do it, right? We started worrying a little bit. All these things, you start to worry. If you're a good scientist, you're going to worry about your measurement, right? And so we started worrying about cutting. We get this really nice non-magnetic metal film for these things, beryllium copper or silver, not silver, phosphor bronze. We used MP35N before too. And they're very non-magnetic, but then you're cutting these things with a metal pair of scissors, and are you transferring magnetic material onto the edges of your cantilever that you can measure? So we bought ceramic scissors to cut these things out with. You know, did it make a difference? I don't know, but sometimes you just find a way so you can stop worrying about a problem. So you can put, if you put the sample on the very tip, obviously you get a little more sensitive. If you put it further back on the springboard, it's not going to be quite as sensitive. So you can choose your also what angle you put this thing at. So a lot of times we'll measure these things on a rotator so that we can measure the angular dependence of this material. So if you're thinking about some material that's quasi-two-dimensional or has a Fermi surface that you care about, you can measure the angle. Have they had the Fermi surface talk yet? It's next. Okay, so you will learn all about doing this, but these make very nice ways to measure the Haas van Alphen and look at the Fermi surface of materials, so you can measure that. But obviously, as you're changing your sample in that magnetic field, you're changing the angle of the magnetization with the field, and you're changing your sensitivity and all of those different things. So you can have these different shapes where you can have potentially a springboard torque, or you can have a twisting torque. You can make a shape that looks more like this, where you just have the springboard torque and not the twisting torque, or less of the twisting torque. Or you can make a shape where you have no springboard effect and it's all constrained to be twisting. Okay? Some of the earliest works were people that just put wires on their samples and then let the sample dangle out in the magnetic field above a capacitance plane and measured the capacitance of the sample while they were measuring resistance in the magnetic field. Okay? And it worked. Okay, so we're like, but it works. Okay, so one of the nice things about this technique is that it does work, and it's very simple and straightforward. So if you're measuring with a capacitance and a metal film, you use a capacitance technique. You have to worry about eddy currents. There's a background due to the gravitational force. There can be mechanical noise due to vibration isolation. So you can use a GR bridge, which was always my favorite technique. Use an external oscillator and a lock-in amplifier. You can get pretty fast data acquisition. Works extremely well. You can use a Wien bridge. I've never done that. And then a lot of people use an automated AH bridge. So this is a capacitance bridge, but it's automated, and it automatically balances, and you hook it up to your sample. For some reason, this doesn't seem to give as good data as the GR bridge in some setups. So you can have a diamagnetic effect. If I'm sweeping the magnetic field, I can induce currents in your film, in your cantilever, okay? And that can have a diamagnetic moment. So it's something to worry about if you are trying to sweep very quickly. You can induce currents into these things and have an effect. This is especially important in a pulse magnetic field. Metal film cantilevers don't work well in pulse magnetic fields. All right, so another way to do this is with a piezoresistive cantilever. A favorite technique is to use an AFM tip. So this is a commercial AFM tip that has two piezoresistive bridges on it, and a springboard with the AFM tip sticking out of the one. So as I bend that tip down, I get a piezoresistive change in the resistance of the piezoresistive element down here, and I can measure that. I have two of these, which is really nice because it means that I can put them into a circuit, and they both are nominally made exactly the same. They're thin films, okay? So they have nominally the same magnetoresistance. They have nominally the same temperature dependence, okay? So as I change the temperature, I'm not worried about what's the temperature change. I'm just worried about how much is the piezoresistance change in that sample. I'm balancing out the temperature dependence and the magnetic field dependence of those piezoresistive elements in a bridge circuit. Okay, and all I can do then, all I have to worry about is how much that cantilever is moving, and then how much that is causing a change in the resistance. Okay, so this can be extremely sensitive. It works really good, but as you can imagine, this is 100 microns here, so you're not going to put a big honking sample on there. In fact, if you try to put a big honking sample on there, it will break off. It will shear, okay? But they work really good for small samples. There's been a lot of work done at the MagLab with this technique. So here you can see some de Haas van Alphen measurements up to high magnetic fields, and as they rotate the sample, you can see the different parts of the Fermi surface showing up. Okay, so here's the setup over here. You glue your sample to to that springboard out there, and they're set up for a pulse magnet. These actually do work well in pulse magnets. I think the next one shows. Does it? No, sorry. So typically we do set these things up in a bridge circuit so that the two sides are the different sides of the bridge, and all you're looking at is the change due to the torquing of your sample on the moment. Okay, they work really good for small moment samples, low temperature heating of the piezoresistive element. So if you try to drive these things too hard, you can get low temperature heating. So don't drive them too hard, and it's not that hard to do. So applications of torque magnetometry: fermiology, magnetic phase transitions, magnetization, anisotropy, superconductors, Vortex anisotropy. Notice that I didn't talk about absolute magnetization anywhere. It can be done to try to calibrate these things, but it really doesn't work very good. Okay? The nice thing is, as Dave will tell us next, I believe, when you're doing fermiology, if you're measuring quantum oscillations, the absolute magnetization of the quantum oscillation really doesn't matter that much. So the sensitivity of these devices works really well. If you care about what's happening in a magnetic field and not the amplitude of what's happening in a magnetic field, they work really good. So if you care about a magnetic phase transition and where that phase transition is happening, okay, but you don't necessarily care about how big that phase transition is, this works really great, okay? But if you care about the absolute moment of that phase transition, then it can be kind of difficult to calibrate these things out. And when I say kind of difficult, I mean it's not really. All right, so here are some typical setups here. There is a beryllium copper foil that's stuck into a little spacer. So you have an interchangeable spacer that puts up above the another foil on the bottom that makes the capacitance plate, and then you can screw these things down, and then it goes into a rotator. So that's sort of a typical setup, and you glue your sample on this. So you can cut these things out of different types of foil, stick it into a standard setup, and off you go. So this is the commercial AFM tip, a Seiko PRC 120, and you can see the tip sticking. Can you see the tip sticking out? I guess that's the tips. The tips are down there. Okay. Anyway, that's the setup there. We had there was a company that was making some commercial silicon beam cantilevers. The company's gone out of business now, but we had some of these at one point. And the idea was that you had these loops on either side of the cantilever, and so as you measured it wasn't a piezo element, it still measured capacitance, but as you measured the capacitance of this thing, you could measure this way, or this way, and you could put feedback current into those loops and run this thing then like you did a SQUID, as a flux transformer, and keep the cantilever at a zero position. As it started to tip, you would put current into that loop and keep it there, and so then you'd have a higher, you'd still have the same sensitivity, but you'd have a higher dynamic range, okay? These were very expensive, and they broke really easily, and they didn't work. But one day, one of you guys can make these work. It's a great idea. So there's lots of other ways to measure magnetization. I'm gonna just run through a few that you might run into, but I'm not going to talk about them in any detail. There are flux gate sensors that you can buy commercially, and they work really well. They're very sensitive. They're not really applicable to high magnetic fields. You can take a Hall sensor and then put your sample on it, and then as the flux from your sample bends into the area of the Hall sensor, you can measure that. So let me summarize now, and I'm a little early. The sensitivity when you're measuring susceptibility, at high fields you can get 10 to the minus 9, typically 10 to the minus 4 to 10 to the minus 6. Wide dynamic range, they work good for phase transitions, spin glasses, super paramagnets, superconductors to Hofmann-Alfvén. The instrumentation can be demanding. They work well at low temperatures and high pressures. They're not quite absolute magnetization, but you can get absolute magnetization if you're willing to calibrate it, okay? Torque can be extremely sensitive, okay? And at high fields, more sensitive than a SQUID. The dynamic range can be narrow to very narrow. They work great for de Haas-Van-Alphen oscillations, for phase transitions, magnetic anisotropy, superconductors. For a polycrystal, you get a small signal. They're difficult to calibrate. You can read that as impossible. We still haven't been able to find a way to make them work with a pressure cell, even though Stan keeps trying a lot. So VSM has a wide dynamic range. It works for all of the things above. It gives you absolute magnetization. It's not terribly sensitive. The field gradients, or the stray field above the hybrid magnet, means that it won't work in the hybrid magnet, but you can do high pressures. Okay? So these are the different techniques that are useful here at the MagLab. If you added SQUIDs into there, we do have lots of SQUIDs all over the MagLab, and they work really well. They only go up to 7 Tesla. Okay? We did try to make a SQUID work at higher fields up to 18 Tesla, and we think you can make it work to even higher temperatures, but it's hard. and we kind of said, oh, that's hard, and we did other things. So, any questions about magnetization? Yes?
I just want to check my understanding.
Uh-huh.
The reason why you have a capacitance bridge is to get rid of the DC signal where you're not interested in the high voltage.
So you're talking about for the torque measurement? Yes. So what you're trying to measure capacitance, right? And capacitance is, you know, if I hook up a capacitance meter, I measure 3 picofarads or 3.2 picofarads. But all of the change in these things is in like the 6th digit, okay? The nice thing about capacitance is I can measure it really accurately. And so I can hook up a capacitance bridge and measure very small changes in capacitance that correspond to very small changes in the moment of the sample. Okay, so in fact, do we have a talk on dilatometry this week? So one of the techniques that we use at the MagLab are dilatometers. So we have one set up that is made by George Schmiedeshoff, and there's a really nice RSI. Recommend that you go read it. But you can put your sample in there, and a tip comes down, and you have these 2 capacitance plates above it. And measuring the capacitance changes in those 2 plates, you can measure sub-angstrom resolution. Okay? So you can measure really small changes in capacitance. And so using a capacitance bridge, you can get wonderful signal to noise. In fact, we were measuring with the Cambridge group, Gil and Zarich, and he was amazed. We were on the hybrid magnet. You know, the water's roaring. The thing's sitting out there, and we had great signal to noise. And he was just amazed that we could get that kind of signal to noise in this measurement. And it's the resonant frequency of that arm doesn't really couple well to the frequency of the water that's running through the magnet. So it really doesn't seem to care that there's all this other vibration in the magnet. It just kind of sits and hangs out there. So we get really, really good sensitivity with torque measurements. People are amazed. And I'm still amazed that other magnet labs in Europe aren't doing this more. So, but if you care about absolute magnetization, it sucks. But if you care about sensitivity, it's amazing. So at the start, I mentioned 2 different statements, right? I can't even remember what they are now. I must be getting old. Something about every measurement perturbs the system. So if we go through these 2 different things, if I'm looking at a torque measurement, how does the measurement perturb the system? So I put this thing in a magnetic field. The magnetic field changes, and what happens to the cantilever? It bends. That's right. Now my sample is at a different angle than it was, right? I have perturbed the system. If I'm measuring very small, very tiny changes in angle, okay, and my cantilever is making very small, very tiny changes in angle, it gets mixed up, right? And we've actually had that before, where things kind of were popping around, and we realized the angle of our sample was changing, and it was changing in sort of an avalanche sort of way, So we were perturbing the system, okay? So what are some ways the other measurements perturb this? How does an AC susceptibility, how does an AC septometer perturb the system? What's that? You can heat it, that's right. Let's say I have an insulator, so I'm not heating it. Yeah. How am I exciting it? That's a good point.
What are you doing to the background magnetic field? How do you get a signal?
Right. I have a magnetic field that I'm applying for my magnet, but I'm oscillating a field too, right? If I have a very sharp transition, right, what happens when I'm oscillating that field through the transition? It's going bang, 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 right? So you have to, if you have a really big excitation, right, you're smearing out the magnetic field that you're looking at, okay, as you're sweeping through. You can have smaller and smaller excitations, but that means my signal becomes smaller and smaller, okay? So you're perturbing the system because you're oscillating the magnetic field in order to measure the magnetization of the sample, okay? VSM, how am I perturbing it? Same thing, right? You're moving that sample in a magnetic field, and it's not homogeneous. So you are changing the magnetization of the sample because it's seeing different magnetic fields as it's vibrating up and down, okay? So those may be small, and they may not affect your sample, or they may be big compared to what your sample is doing. So everything you measure, you have to worry about, how is this affecting my sample? And is it really, am I really measuring what I think I'm measuring? Yep.
And if you sing, your pickup call or passive, I mean, they're not active. How do you, I mean, they're not.
Right, but my sample is moving up and down in a magnetic field, right? So my sample is experiencing different magnetic fields, and I'm I'm different magnetic fields and saying that's one magnetic field. So I'm, in some sense, smearing out the magnetic field that
Again, overall magnetic field, or you talk about this?
right. If I have a magnet, if I have a magnet, right? If you look at the profile, if you go to our website and you look at the profile magnetic field versus the longitudinal direction, right? At the field center, there's going to be an area that's relatively flat, but it's still not flat, right? There is still a profile. So at the very center, yeah. Yeah, so here's the magnet. So I have the maximum magnetic field, and then it goes down. But in this region here, it's still curving, right? So it's homogeneous to a certain degree over a certain area. But if your sample cares about that small little bit of field change here, right, this change between here and here, right, that you're moving it, then you're perturbing your sample, right? Your sample may not care. It may not be a big deal at all.
So actually, you're using just 1 millimeter amplitude.
That's right. That's right. But you're still, if you're doing an extremely sensitive measurement, you can still be perturbing it, okay? So everything you do, SQUIDs tend to be pretty soft, but I'm still moving through a magnetic field, and that magnetic field is not perfect.